In order to arrive at similar numbers as Helvetas above, we can dig into these assumptions and do a more in-depth analysis with ASCE 7, Chapter 29 for other structures. We'll use the W1 walkway detail as an example because this has the most surface area for wind pressure to develop. Now, first, we'll start at the top level. Our drag force perpendicular to the bridge, F, we'll find with the equation 29.5 for open signs, trussed towers, or lattice frameworks. The variables here are QZ, the velocity pressure evaluated at height Z, gust factor, G, from section 26.3, force coefficient, CF, that can be found based on figures in the code, and AF, the projected area normal to the wind. And once again, we're using the W1 walkway detail. So first, we're going to go in and find QZ, the velocity pressure, at height Z. And this is our equation for QZ given in 29.3.2 with more variables that you need to look up in the code, the wind directionality factor, KD, the velocity pressure exposure factor, KZ, the topographic factor, which is actually a reduction based on topography, and our basic wind speed. So we'll take KD as 0.85 for open signs and lattice structures, and we'll take KZ as 1.27 from table 29.3-1 for exposure category D, and we'll assume our deck is 50 feet off the ground. We'll assume the reduction conditions aren't met, so we'll take KZT equals 1, and our our basic wind speed will be 100 miles per hour or 160 kilometers per hour. So multiplying all of these together, we get 27.6 pounds per square foot. And we can go back to that 29.5 for other structures equation and calculate our force. But first, we need to take a step back. So we'll go and we'll get our gust factor from section 26.9 of 0.85. And then when taking our CF value, we're actually going to assume this is a solid, flat-sided surface. And we're going to adjust the amount of, we're going to adjust that AF based on how much solid area there is to gross area in a section of walkway. So we'll take CF as 1.6 for simplicity for a flat-sided sign. And then we'll take a look at our walkway detail here. And we can see that we have approximately 0.35 meters squared per 1.1 meters squared of gross area. So what that means is for a height of 1.1 meters and per 1 meter along the walkway, we have a gross area of 1.1 meters squared. And in that gross area of 1.1 meters squared, we have an effective area that is a combination of the fence, the deck, and the cable. The fence we can take as that 1 meter multiplied by the height of the fence, which is 1.1 meters, times 2, because we're passing through two fences, two sections of fence, and divided by 8.83, which comes from a chart that is in the course textbook. It's specific for this type of fence based on the mesh and the pattern of the mesh, how much solid area there is to gross area. The deck, because the decking extends the full length of that 1 meter, we can just take as 1 times the thickness of the deck. Then we will add the area of 1 crossbeam and the area of 1 nailer that is captured in that area. So I've kind of drawn this a little misleading. It'll just be 1. Then the area of the cable will be the actual area of the cable times 2, because we're passing through 2 cables, times 1, which is 1 meter length that we're taking. And this will actually just be the diameter of the cable, because in looking in this section, we are just looking at the diameter of the cable. And then our AF we can take as our epsilon factor times our height times 1. And we can multiply that all together to get a force of 16 pounds per linear foot, or 0.77 kilonewtons per meter. And finally, we need to adjust that by the primary wind load factor from 2.4.1 of the code if we're using ASD, which we are here, at least for the Helvetas numbers, and we'll get a factor of 0.463 kilonewtons per meter.